Welcome back to The Explainer. Today, we're doing something a little bit different. We're literally taking a standard geometry chapter and lifting it right off the textbook pages to look at the world around us in a totally new way. It's incredibly easy to just think of geometry as a bunch of abstract rules trapped inside a math classroom. But honestly, that couldn't be further from the truth. The reality is, math is completely alive. It's in the breathtaking historical monuments we go visit. It's in the cardboard boxes we eagerly open, and it's even in the physical stretches we do with our own bodies. So let's dive right in and decode the shapes that make up our world. Here is exactly how we're going to break it all down today. We'll start with number 1, building the 3D world. Then 2, unfolding shapes with magic nets. 3, where lines meet in angles. 4, the secret to strong shapes. And finally, 5, the perfection of circles. All right, let's kick things off with Section 1, Building the 3D World, Geometry in Real Life. Take a second to really think about the buildings that surround you every single day. I mean, they didn't just magically appear, right? They completely rely on fundamental geometric principles. Just look at the sheer contrast here. On one hand, you have the majestic Charminar, a soaring, highly complex structure packed with towering pillars, arches, and intricate domes. And on the other hand, you have a beautifully simple traditional thatched hut built with a curved roof and a cylindrical base. Now, despite looking absolutely nothing alike, both of these architectural marvels rely on the exact same universal language of geometry just to stay standing. And it's actually fascinating how easily we can break down those massive, complex structures. Just check out Diksha here. She was super inspired after visiting some incredible monuments in Delhi, so she decided to build a model of the India Gate using simple wooden blocks. And it turns out, even the most incredible World Heritage sites can be deconstructed exactly like this. Take the Qutub Minar, for example. It's literally the tallest building in the world made entirely of bricks. It boasts 5 stories and a staggering 379 stairs. Yet, fundamentally, it's really just built by stacking simple geometric blocks together to form solid bases, sturdy pillars, and protective roofs. So the absolutely crucial point here is understanding the basic anatomy of those building blocks. Every single 3D object, whether we're talking about a towering pyramid or a long rectangular prism, is defined by 3 main properties. First up, we have the faces. Those are the flat surfaces you can actually touch. Second, we have the edges, which are just the straight lines where 2 of those faces meet. And finally, the corners, which are those pointy little spots where the edges all crash together. Mastering just those 3 properties gives us the key to understanding literally any 3D structure on the planet. Moving right along to Section 2, Unfolding Shapes, Magic Nets. Okay, now that we've built the 3D world up, let's have some fun and reverse engineer it by flattening it right back out. If you've ever taken a cardboard delivery box and flattened it out for recycling, well, you've already engaged in this exact mathematical concept. This flattened blueprint you see is what we call a net. It's essentially a magical 2D map of a 3D object. And the coolest part is that if you take this flat piece of paper and fold it right along those dotted creases, the whole thing springs back up to give you a fully formed 3D shape all over again. Actually, I want to pause for just a second and ask you this directly. If you were to mentally fold those side flaps up along the dotted lines and then fold the top parts right over, what 3D shape does this net make? Being able to mentally fold shapes like this in your head is seriously like a superpower for spatial reasoning. All right, let's zoom in a bit for Section 3, where lines meet angles. So we've looked at massive structures and full 3D shapes, but now we really need to zoom in close to the exact intersections where those edges collide. Whenever lines meet, they create angles, and there are 3 core angles you absolutely have to know. First up is the right angle. This is that perfect square corner you see 100 times a day on a window pane or the corner of your textbook. Next, we have the acute angle. Think of this as the smaller, sharper angle. It's any angle that's squeezed tighter and is less than a right angle. And finally, we have the obtuse angle. This is the wider, much more open angle, meaning it's stretched out far wider than a right angle. And honestly, you don't even need buildings to see this stuff. Just look at these stick figures doing some yoga postures. Math isn't just about rigid objects. Our very own bodies naturally create these angles all the time. Think about it. When you bend your knee slightly, you're making an acute angle. When you stretch your leg out super wide, you're forming an obtuse angle. And standing perfectly straight and bending at the waist, that can create a perfect right angle. Geometry is quite literally in motion. Which brings us to Section 4, the secret to strong shapes.
Have you ever wondered why some buildings stand perfectly for centuries while others collapse? The answer actually lies in the structural integrity of the shapes themselves. Imagine for a second you build a little rectangular shape out of drinking straws, using bits of clay at the corners to hold it together. Initially, it holds those beautiful right angles. But what happens if you gently push just one of its sides? It totally shifts. It completely loses its right angles and warps into a new slanted shape. It's weak. Now take that exact same clay and straw and build a triangle. Push it. What happens? Absolutely nothing. The triangle is completely rigid. Its shape simply does not change when pushed. And that rigidity right there is the ultimate secret to strong building design. Whenever architects need things to stay standing, they always rely on the mighty triangle.
And that leads us to our final stop, Section 5, the perfection of circles. Moving away from the sharp, rigid intersections of triangles and squares, we enter the totally elegant, continuous flow of circles. Just look at the sheer uniqueness of a perfectly round circle. While we spent the whole first part of this explainer talking about faces and edges and corners, the circle just completely breaks all the rules. It features exactly one perfectly curved face, absolutely zero edges, and literally zero corners. It is just flawless, continuous geometry. But that raises a big question. How do we measure something that has no straight edges? Well, let's say you cut a circle out of a piece of paper and fold it precisely in half. That crease right down the middle, that's called the diameter. And no matter how many times you fold it across, all of those diameters will intersect perfectly at the exact center point of the circle. Now, if you measure the distance from that center point straight out to the border, that length is what we call the radius. As we wrap up today's explainer, I want to leave you with a direct challenge. I want you to look away from whatever you're watching this on right now. Scan the room you are currently sitting in. Look at your desk, the walls, the furniture around you. Can you find an object, or even a pattern, that features exactly two right angles, one acute angle, and one obtuse angle? Applying these rules to your immediate environment is hands down the best way to prove that the geometry from this chapter truly is absolutely everywhere. Thanks so much for learning with me today, and keep exploring the shapes around you.